In this video series, we will discuss E2 reactions. This video series builds on the ideas we covered in the previous series on SN2 and SN1 reactions. If you find that the video explanations move too slowly, you could simply try the problems in the problems document. Check your answers against the answers document, and when necessary, skip to the video explanations for the particular problems that are giving you difficulty. Now, let's begin by discussing this problem. Please pause the video and try this problem on your own. Okay, well, now we can discuss the solution to this problem together. Let's start by numbering all the carbons, including this one. Next, we have to decide which atoms will be participating in the mechanism and what roles they will play. Well, the atom that is most likely to participate in the mechanism is this O-, and the reason for that is because it has a formal charge. The atoms that are most likely to participate in a mechanism are the atoms with a formal charge. So we predict that this O- will participate in the mechanism. Now, what role do we expect the O- to play in the mechanism? The negative formal charge makes the oxygen want to donate electrons. So this oxygen could play the role of nucleophile or base. Because both a nucleophile and a base are electron donors. Atoms don't like having formal charges. Atoms prefer to be neutral. So when an oxygen has a negative formal charge, it wants to donate electrons to get rid of that negative charge and get back to neutral. Remember that electrons have a negative charge. So you can get rid of a negative charge by giving away some of your electrons. The most important factor in organic chemistry is formal charges, because formal charges are our most important tool for predicting what role atoms will play in a reaction. Here we used the negative formal charge on the oxygen to predict that the oxygen can play the role of nucleophile or base. Now, which is it? Will the oxygen be a nucleophile or a base in this particular mechanism? Well, we will figure that out shortly. Remember, both a nucleophile and a base are electron donors. So a negative formal charge can make an atom want to behave either as a nucleophile or as a base. Now, what other atoms do we expect to participate in the reaction, and what role do we expect those atoms to play? Well, you should have memorized that neutral chlorine, neutral bromine, and neutral iodide are good leaving groups. So we expect this neutral bromine to play the role of leaving group. Carbon 2 is attached to our leaving group, so I'm going to label carbon 2 as the alpha carbon. The alpha carbon is the carbon that's attached to the leaving group. This is the definition of alpha carbon that is helpful in this context. We need to know whether our alpha carbon is primary, secondary, or tertiary. So what do you think? Here's the answer. This alpha carbon is secondary. A secondary carbon is a carbon attached to two carbon chains. Carbon 2 is attached to two carbon chains. A carbon chain that begins with carbon 3 and another carbon chain that consists of carbon 1. Notice that even a single methyl group can count as a carbon chain for this definition. Write down that we have a secondary alpha carbon. We should recognize that this starting material is an alkyl halide. An alkyl halide is a halogen attached to an alkyl group. The halogens are the elements from the 7th column of the periodic table, such as chlorine, bromine, and iodine. And an alkyl group is a carbon chain. Well, this molecule has a bromine connected to a carbon chain, so it's an alkyl halide. Now, our next step is to determine the mechanism for these starting materials. How do we do that? Well, the best way to determine the mechanism for an alkyl halide is to use a table. Here is a handout that contains a table for choosing the mechanism for alkyl halides. You can find a link to this handout in the video description box, and now would be a good time to click that link and print out this handout so that you can have this handout in front of you as you're working through this video series. You can see from the title of the table that this is a table that we can use for determining the mechanism for alkyl halides. Which row of the table applies for this problem? Well, we have a secondary alpha carbon, which means that we should use the middle row of the table for a secondary alpha carbon. Which column of the table applies for this problem? Well, our nucleophile or base is O-. O- is in the right-hand column of the table. So we're applying the right-hand column of this table because we're using O- as our nucleophile or base. Therefore, the table predicts that the mechanism will be E2. Write down the name of the mechanism. Remember that the most important factor in organic chemistry is formal charges. Notice that in this table, there's a huge difference between a neutral oxygen and a negative oxygen. If we were dealing with a neutral oxygen, we'd be in a completely different column of the table. So it's crucial to notice that we have not just an oxygen, but a negative oxygen. That's why we're using the right-hand column of the table. So we have seen that the way to determine the mechanism for alkyl halides is to use this table. But that means that if you want to be able to determine the mechanism for alkyl halide problems on your exams, you're going to have to memorize this table. Now we have to try to draw the electron pushing arrows for an E2 mechanism. Well, are you familiar with E2 mechanism? How many steps are there in an E2 mechanism? Well, if we go back to this handout, notice that there's a separate box that summarizes what happens in E2 and related mechanisms. So here from the handout, you can see that an E2 mechanism consists of one step. There is one step in an E2 mechanism. What happens during that one step? Well, you can see that it's quite complicated. Three things happen. In the single step of an E2 mechanism, the base takes the beta hydrogen, and simultaneously, a pi bond forms between the alpha and beta carbons, and simultaneously, the leaving group leaves the alpha carbon. You can see that the alpha carbon and the beta carbon play an important role in an E2 mechanism. We've already labeled our alpha carbon, but who is the beta carbon? Do you know? We've learned that the alpha carbon is the carbon attached to the leaving group. The beta carbon is defined as a carbon attached to the alpha carbon. So this molecule has two beta carbons. Carbon 1 is a beta carbon because it's attached to our alpha carbon, and carbon 3 is a beta carbon because it's attached to our alpha carbon. Notice that carbons 5, 6, and 4 are not attached to carbon 2 directly, so they're not beta carbons. Alpha and beta are the first two letters in the Greek alphabet. Alpha and beta are adjacent to each other in the Greek alphabet, and an alpha carbon and a beta carbon are carbons that are adjacent to each other in a molecule. Our word for alphabet comes from the first two letters of the Greek alphabet, alpha and beta. Now, which of these beta carbons should we use in our E2 mechanism? Carbon 1 or carbon 3? Well, notice that in the E2 mechanism, we need the base to take the beta hydrogen. A beta hydrogen is a hydrogen attached to a beta carbon. Well, notice that carbon 1 is attached to some hydrogens. Carbon 1 is attached to 3 hidden hydrogens. But carbon 3 is not attached to any hydrogens. There's no room for any hydrogens on carbon 3 because we can see that carbon 3 has bonds to 4 other carbons. Carbon 3 is bonded to carbon 5, carbon 6, carbon 4, and carbon 2, so there's no room for any hidden hydrogens on carbon 3. Remember that a neutral carbon should form 4 bonds. So carbon 3 is a beta carbon, but carbon 3 is not going to participate in this E2 mechanism because carbon 3 doesn't have any hydrogens. So actually now I can erase this beta label because we're not going to be using this beta carbon in our E2 mechanism. Now we can decide whether we're going to use the O- as a nucleophile or a base for this reaction. We know we're doing an E2, and we know that an E2 mechanism uses a base, not a nucleophile. So we know that the O- in this reaction will act as a base, not as a nucleophile, because E2 uses a base, not a nucleophile. Furthermore, from our table, we can see that O- is a strong base. The table tells us that O- is a strong base. So I label the O- as SB for strong base. Now a base takes a proton from an acid, so we have to decide which atom is going to act as the acid. The acid is the atom that gives away the proton to the base. Well, remember that our base is going to take the beta hydrogen, the hydrogen from the beta carbon. That means carbon 3 is going to act as our acid. I've labeled this beta carbon Wa for weak acid. It's a fact that you should simply memorize that the beta carbon in an alkyl halide is a weak acid. This beta carbon is going to act like an acid because it's going to give away a proton to the base. Strong means reactive, and weak means unreactive. Because our base is strong, it's reactive enough to react even with a weak acid. Now it's time to draw the electron-pushing arrows for the E2 mechanism. Our first arrow has to show the base taking the beta hydrogen. Do you know how to draw that arrow? Remember that a base is an electron donor. That means that the base has to go at the beginning of the series of arrows to show that the electrons are moving away from the base. Remember that the electron-pushing arrow shows the movement of the electrons. So this electron-pushing arrow shows us that electrons are moving away from our base. That's what we want. A base is supposed to donate electrons. Now, who do we put at the end, at the head of this arrow? Well, the base is donating electrons to take a proton from the acid. So at the head of this arrow, we have to put the proton that the base is taking from the acid. Notice that we had to draw in this hydrogen, which was not shown in the original picture of the molecule. I'm going to be using these terms to describe our electron-pushing arrows. This is the tail of an electron-pushing arrow. This is the head of an electron-pushing arrow. Electrons move from the tail of an electron-pushing arrow towards the head of an electron-pushing arrow. A base goes at the tail of an electron-pushing arrow to show that the base is an electron donor. And at the head of this electron-pushing arrow, we put the proton that the base is taking from the acid. So now we've drawn the arrow that shows the base taking the beta hydrogen. This is the arrow that shows the base taking the beta hydrogen. Now we have to draw an arrow to show the pi bond forming between alpha and beta carbons. Well, remember that a hydrogen can only have one bond at a time. If this hydrogen is going to form a new bond to this oxygen, the hydrogen will have to break its bond with carbon 3. By the way, after I had finished recording most of this video, I realized that I had accidentally misnumbered this carbon at some point. Originally, this carbon was supposed to be numbered as carbon 1. But at some point, unfortunately, I accidentally erased the number 1 and accidentally replaced it with the number 3, and I didn't notice that until I'd recorded a lot of the video. So unfortunately, in the next segment of the video, I'm going to be referring to this carbon as carbon 3. Obviously, that's not a very good habit because this is the carbon that's supposed to be carbon 3. You shouldn't use the same number for two different carbons in the same molecule. But unfortunately, that is a mistake I made the first time I recorded the video, and I hope you won't find that too confusing. Now we have to draw an arrow to show the pi bond forming between alpha and beta carbons. Well, remember that a hydrogen can only have one bond at a time. If this hydrogen is going to form a new bond to this oxygen, the hydrogen will have to break its bond with carbon 3, and that's going to free up the electrons in this bond. What can we do with the electrons that are freed up from that bond? We can use them to form the pi bond between the alpha and the beta carbon. So here's the electron pushing arrow that shows us freeing up the electrons between the beta carbon and the beta hydrogen, and using those electrons to form a pi bond between the alpha and the beta carbons. Notice that the head of this electron pushing arrow should go between the alpha and the beta carbons. That's the way that you show that you're forming a pi bond. This arrow would be wrong. This is not the correct way. This is not the correct way to draw an arrow that shows that you're forming a pi bond. To form a pi bond, you should put the head of the arrow between the two atoms that you're forming the pi bond between. So this is the electron pushing arrow that shows the pi bond forming between the alpha and the beta carbons. And lastly, we need a third electron pushing arrow to show the leaving group leaving the alpha carbon. Do you know how to draw that electron pushing arrow? You probably do. A leaving group receives electrons to leave an atom. So we have to put this leaving group at the head of an electron pushing arrow to show that the leaving group is receiving electrons while it breaks its bond with carbon 2 and leaves carbon 2. From this electron pushing arrow, you can see that a leaving group really does receive electrons while it leaves an atom. You can see that an E2 mechanism is quite complicated. 3 separate things happen simultaneously in the same step for an E2 mechanism. So we need to draw 3 electron pushing arrows simultaneously for the same step for an E2 mechanism. It took me a while to draw all the arrows in this mechanism because I was discussing each one carefully, but obviously you want to keep practicing until you can draw these arrows more quickly and efficiently. Remember that the most important factor in organic chemistry is formal charges, because formal charges are our most important tool for drawing reasonable electron pushing arrows. So are these electron pushing arrows consistent with this formal charge? Does it make sense to put a negative formal charge at the beginning of the series of arrows? Yes, absolutely. An atom with a negative formal charge wants to donate electrons, so it makes good sense that this O- is at the beginning of the series of arrows. If we had placed this O- at the end of the series of arrows, or in the middle of the series of arrows, that would be a strong clue that we had made a mistake. An atom with a negative formal charge wants to donate electrons, so an atom with a negative formal charge should go at the beginning of a series of arrows, not at the end of the series of arrows. Now that we have drawn the electron pushing arrows for this step, it's time to draw the products from this step. Here are the rules for using electron pushing arrows to draw the products of a mechanism step. Every electron pushing arrow tells you to erase a bond, or to draw a new bond, or both. So what do you think this electron pushing arrow tells you to do? I hope that you think it's intuitive that this arrow tells us to draw a new bond between the oxygen and this hydrogen. So here I've drawn a new bond between this oxygen and this hydrogen. Earlier, we numbered all the carbons in the starting materials, and we should continue to number all the carbons in the products. But that only helps if we numbered the products consistently with how we numbered the starting materials. So I'm going to call this carbon 7 to be consistent with how I numbered it in the starting materials. Numbering just helps students to make fewer mistakes. Technically, for this arrow, we've used this rule. You should form a sigma bond when the arrowhead is pointing to an atom which was not already sharing the electrons at the tail of the arrow. I know that sounds a little bit complicated, but the way that it applies here, notice that at the head of this arrow we have the hydrogen, and at the tail of this arrow we have this lone pair on the oxygen. Well, notice that in this picture, the hydrogen is not yet sharing the electrons at the tail of the arrow. In this picture, the hydrogen is sharing those electrons. In this picture, the hydrogen is sharing those electrons in a covalent bond. But in this picture, the hydrogen is not yet sharing the electrons at the tail of the arrow. That's the situation when an arrow tells you to form a sigma bond. I know this rule is a little confusing. I'm going to discuss this rule a little bit more in the next video, but for the time being, I think it's pretty intuitive that this is an arrow that tells us to form a bond between the oxygen and the hydrogen. Now, the most important part of our products to get right is the formal charges. Because this oxygen is at the beginning of the series of arrows, the oxygen is losing electrons. The oxygen started negative and it lost electrons, so it should become one step less negative, so we changed the formal charge on this oxygen from negative to neutral. For every mechanism step, you should make the atom that loses electrons at the start of the chain of arrows one step less negative. Now we can work on this second arrow. Again, every arrow tells you to erase a bond, draw a bond, or both. So what do you think this arrow tells you to do? Is it intuitive that this is an arrow that tells us both to erase a bond and to draw a new bond? The tail of this arrow is on the bond between carbon-3 and the hydrogen. That tells us to erase the bond between carbon-3 and the hydrogen. And really, I already kind of erased that bond when I moved the hydrogen into this position. Now, the head of this arrow is pointing to the bond between carbon-2 and carbon-3. That's the situation when you need to form a pi bond. So we need to form a pi bond between carbon-2 and carbon-3. Form a pi bond when the arrowhead is pointing to a bond. So this arrow told us to form a new pi bond between carbon-3 and carbon-2. So now we've dealt with this arrow. This arrow told us to break the bond between carbon-3 and the hydrogen and to form a new pi bond between carbon-2 and carbon-3. Now we have to work with this electron-pushing arrow. Does this arrow tell you to erase a bond, draw a bond, or both? Well, this is an arrow that tells us to erase a bond using this rule. Because the tail of this arrow is on this bond, that tells us to erase the bond between carbon-2 and the bromine. And I actually already went ahead and already did that. Furthermore, since the bromine is at the end of the series of arrows, the bromine is going to be gaining electrons. The bromine started neutral, and it gained electrons. So the bromine should become one step more negative. So we should change the charge on the bromine from neutral to negative, which I've already drawn here. You should always make the atom that gains electrons at the end of the chain of arrows one step more negative. So we've changed two formal charges on the bromine, and we also changed the charge on the oxygen from negative to neutral. Do not change the formal charge for any atom in the middle of the series of arrows. The hydrogen and carbon-3 and carbon-2 are all in the middle of the series of arrows, so we didn't change the formal charge on the hydrogen or on carbon-3 or on carbon-2. You change the formal charge at the beginning of the chain of arrows, and you change the formal charge at the end of the chain of arrows. For every mechanism step, that means that you change two formal charges. These are the rules for using electron-pushing arrows. I took my time and drew this product quite slowly because I was trying to explain the rules for using electron-pushing arrows, and clearly you need to keep practicing until you can draw products using this process much more quickly and efficiently than the time it took me to talk through the process this first time. Here is a handout, another handout, that contains the rules for using electron-pushing arrows to draw the products of a mechanism step. You can access this handout by clicking the link in the video description box. I mentioned that you should number all the carbons in the starting materials and the products consistently. That helps students to avoid making mistakes. I didn't really follow my own advice here. Originally, I had, did you notice? Originally, I had labeled this carbon as carbon-1, but somewhere along the way I made a mistake and it changed to carbon-3. That's no good because I've already used that label carbon-3 over here. So sorry about that. I hope that didn't cause confusion. This carbon should have been labeled as carbon-1 all along. so it should also be labeled as carbon 1 in this picture. Try to maintain consistent labels, consistent numbers for all the carbons in all of your pictures. That helps students to make fewer mistakes. Now, we've finished this mechanism step. Is our mechanism finished completely, or do we need another step? Well, actually, we're done. You can see that we're done. First of all, we expected E2 to only consist of one step, so that's a clue that our mechanism is finished. And furthermore, the usual rule in organic chemistry is that the reaction is usually finished when the main product has no formal charge. That's a good rule for the first semester anyway. So our main product here, I would consider this the main product. Our main product here has no formal charge, and that's a clue that our mechanism is finished. Notice that we can't get rid of all the formal charges. We weren't able to get rid of the formal charge on this bromine, but our main product, so to speak, has no formal charge, and that's a clue that our mechanism is finished. SN2 reactions are actually an exception to that pattern, but this is a good rule to follow for E2 mechanisms. So for both of those reasons, we can be confident that we're finished, and we've finished this mechanism. There was only one step in this E2 mechanism. We said that this starting material is an alkyl halide. What about this product? Do you know what is the name of the functional group in this product? Here's the answer. Our product is an example of an alkene. An alkene is defined as a carbon-carbon double bond. We have a carbon-carbon double bond here between carbon 1 and carbon 2, between our former alpha carbon and our former beta carbon. You need to know that E2 mechanisms produce alkenes. E2 mechanisms produce alkenes. And you should also know that a common starting material for an E2 mechanism is an alkyl halide. We can use an E2 mechanism to change an alkyl halide into an alkene. Here are some guidelines that are useful for drawing E2 mechanisms. We saw what an important role the alpha and beta carbons played in this E2 mechanism. So my advice is that you should always label the alpha carbon and the beta carbon that you're using in your mechanism. We labeled our alpha carbon, and we labeled carbon 1 as the beta carbon because that was the beta carbon that we were using in our E2 mechanism. You will make fewer mistakes for E2 if you always label your alpha and beta carbon. We also used the idea that only a beta carbon attached to one or more hydrogens can be used for E2. Carbon 3 is also a beta carbon, but it's not used for the E2 mechanism because it's not attached to any hydrogens. In an E2, the base takes the beta hydrogen. So only a carbon that's attached to a hydrogen can be a useful beta carbon for an E2 mechanism. Only a beta carbon attached to one or more hydrogens can be used for E2. Remember that a neutral carbon should have 4 bonds total. Carbon 3 was already showing 4 bonds, so we knew there was no room for any hidden hydrogens. Carbon 1 was originally showing only 1 bond to another carbon, so we knew there were room for 3 hidden hydrogens, and we used 1 of those hidden hydrogens in our E2 mechanism. We've seen that even though there's only one step in an E2 mechanism, it's actually quite a complicated mechanism because 3 things happen simultaneously in that one step, which means that you need to draw 3 electron-pushing arrows for that one step. So it's very important now that you pause and memorize these 3 things. You should now pause the video and take as much time as you need to memorize these 3 things that happen during the one step of an E2 mechanism. Each of these things requires an electron-pushing arrow. You have to show an electron-pushing arrow to show the base taking the beta hydrogen. You have to draw an electron-pushing arrow to show the pi bond forming between alpha and beta carbons, and you have to draw an electron-pushing arrow to show the leaving group leaving the alpha carbon. When you feel that you have these 3 ideas memorized, you're ready to proceed to the next video in this series, where you can get some more practice with the E2 mechanism. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen, or by using the link in the video description box. Thank you.